Hi friends, so today I'm gonna show you how to use a IC compiler. So first of all, make sure your Xming is running. Go to the putty. My IC compiler is hosted on this server, so I'm just logging into this server with my credentials. Now before using the IC compiler, make sure you have your Verilog code synthesized using Design Vision and have a netlist file and the SDC file, that is a synopsis design constraint file. These two files are generated as the output of a design compiler. So this is one such design available with me. I have synthesized my mrca.v. This is my Verilog file. I have synthesized this using Design Vision, and this is my constraint file as the output, and this is my netlist file. So I'll be using both of these two files along with the few other technology files so as to generate a layout for this particular design using the standard cells. So the command to launch IC compiler is icc shell GUI. When you launch this command, your IC compiler will be popped up backend. So here is our IC compiler. So before importing those Verilogs and synopsis design constraint, we have to set up the environment using the different technology files. First of all, setup, application setup. Here I'll be browsing the database file which I have used in my DC compiler as well for the synthesis part. So here, IC compiler, models. These are the database files I have used as well in my Design Vision or DC compiler. So I'll be using the same database file in the IC compiler as well. So I have my database file been set up. Thereafter I need to create a library. I usually create a library in the design I'm generating the layout for, which is mrca1. The name of the library you can keep whatever you want. Technology file is again available to you using 19 nanometer technology file. So this is the technology file I'm using. Input file references means the standard cells where they are located, and the compiler will look into that folder for use those standard cells. So they are available. Sorry. Here. I've chosen them to make sure you take this open library check block. Yep, that's it. After this, I need to set up the TLU files. All these files will be available to you through Blackboard. You can download them. For the max, I'll be using CMax. For the minimum TLU plus file, I'll be using CMin. And mapping file is this tech2itf.map. Now after this, we have set up all those environment variables. Now we need to import our Verilog code or the synthesized Verilog. Make sure you are browsing your synthesized Verilog, which is the output of a DC compiler. So this is my synthesized Verilog file. I have put it into it. It will take a while to load that Verilog file. So yeah, this is that Verilog file. It has been loaded. Thereafter I need to upload my design constraint file, that is SDC file as well. So read SDC. I'll be browsing the design constraint file for my present design. Okay, now we proceed to the backend steps. The first step in the backend is floor planning. First we need to create a floor plan. We are using a core utilization 70%, and for the pads I'm using 10 micrometer as the distance. So this is my core area and these are all my standard cells. After that I need to create a VDD and VSS power rails. Next step is create rings under pre-route only. I'm creating a rectangular rings for VDD and VSS. My offset is 1 micron between the two rails and the width for each rail is 3 micrometer. And I'll be using metal 5 and metal 6 for VDD and VSS. Okay, now you can see that these power rails, this is VSS, this is VDD, here this is VDD, this is VSS. They have been generated. Step after creating is we need to create a power straps for both VDD as well as VSS. Metal 5, I'll keep it width as 0.16, 40 power rails with a distance between them 2 microns. Okay, so it has been created. Now your standard cells will be placed into these power rails. So for that, placement, core placement and optimization. Okay, it will take a while. So what it will do, it will put all your standard cells into those. Now they have been routed and have been put into those power rails. Next step is pre-route standard cells. Go into the routing option, uncheck keep floating rail segment and check mark this extend block to boundaries and generate pins and fill empty rows. Again pre-route instances. You need to do nothing, just apply or OK. The last step in the pre-route is we need to give the routing connections. The standard cells has been placed but they have not been connected with each other. So go to route, core routing optimization. Okay, before that there are certain other commands as well. If your design include clock, you can go to the other window and the command is clock opt hyphen fix hold all clocks and report clock tree, which will like show up the clock tree that has been synthesized in your design, and report timing. So it will let you know that in your layout what will be your timing details or what will be your delay. Then you can switch back to the other window, and the final step is routing those standard cells or interconnecting those. Medium, I keep the option as such. Okay, it will again take a while. So this is like your final layout, which houses all those standard cells, and they are being interconnected with each other. If you zoom it out, you can look into, these are all my various standard cells, and they have been interconnected with each other. Now you can export the Verilog file, which includes all those interconnections, parasitics, whatever the thing is. I write it as mrc_icc.v. Okay, and you can export your parasitics as well. SPEF mrca1_spef.spef, which is nothing but just include all those parasite details, and you can import these files further into PrimeTime and other tools for the static time analysis or the power consumption for your chip. Okay, so I have written both of these files. You can also generate a stream or write a stream in a GDS2 format, and eventually can order to any of the foundry so as to design this layout on any of the wafer. So these are the only things that we have required. Thereafter you can save your cell. And exit. Now you can see that these are my parasitic files, and this is my Verilog file at the output of the IC compiler. I can use that file again into the design compiler, and which will get those power, timing and the area details, which are quite exact, because I am generating these from a layout level now. So I have my script with me, synthesize.tcl. Here I've already put up my this Verilog file that I have extracted out of that IC compiler, as well as the name of the top module. So this is the clock pin. This is actually a critical path. I have determined this, that my critical path is from input B0 to the output sum 15 during my synthesis part. So this is how, and here notice that I am using the same database file that I have used in my IC compiler. So rest all the parameters are been set up. I need to run this script. The command is dc_shell -t-f synthesize.tcl. So now you can get all those power, timing, which is 2.70 nanosecond, and area report. Sorry, the name is cell. You may find that these figures are different from the figures that you have extracted when you synthesize your design in the design compiler, because here that time your Verilog file is your own Verilog file, which is written in any of the behavioral fashion or whatever the way you like. But here my input Verilog file is the Verilog file that I have extracted out of that IC compiler. So the results here depicts your post layout simulation. So this is all about the IC compiler is. There is also possibility to do this all step with the help of a script. uh, Maybe we are sharing the script as well for this in the very near future. Thanks for watching.